In the next series of modules, we will look at heat exchangers. First, we will look at the mathematics, just the derivation of equations that are needed to design a tubular heat exchanger. But then we will also work with some examples and see how we can apply mathematics to design tubular heat exchangers.
So first let's see what are some of the assumptions that are made in developing our mathematical procedure. 1. We will assume that heat transfer is under steady state conditions. 2. That the overall heat transfer coefficient is constant throughout the length of the pipe. What that means is that we are dealing with the same type of material used to make our pipes, so it has the same thermal conductivity, and also the inside and outside convective heat transfer coefficients will be the same. 3. We will assume that there is no axial conduction of heat in the metal pipe. In other words, heat transfers only in the radial direction in the pipe, not in the axial direction. And that the heat exchanger is well insulated so that we don't have any exchange of heat with the surrounding air or any other fluid that may be present. So first let's look at a simple energy balance to determine the rate of heat transfer. Now if you look at the fluid that is flowing inside the heat exchanger, and if its temperature changes from some temperature T1 to temperature T2, then we can write a very simple expression that Q, or the rate of heat transfer, equals m dot, which is the mass flow rate, times Cp, that's specific heat of that fluid, times T1 minus T2. So T1 is a inlet temperature and T2 is the exit temperature from our heat exchanger. Now if a hot fluid enters the heat exchanger at location 1 and flows through the inner pipe exiting at location 2, its temperature would therefore decrease from some TH inlet to TH exit. Similarly, if there is a cold fluid, fluid C, that enters the annular space between the outer and inner pipes of the tubular heat exchanger at location 1 and exits at location 2, its temperature will increase from TC inlet to TC exit. So again, by using our simple energy balance, we can write that the rate of heat transfer between the hot fluid and the cold stream is m dot h times Cph times Th inlet minus Th exit, and that equals m dot c Cpc times Tc exit minus Tc inlet, where Cph is the specific heat of the hot fluid and Cpc is the specific heat for the cold fluid. And the mass flow rates m dot h and m dot c are in kilograms per second. M dot h is for hot fluid, m dot c is for cold fluid. Now this heat balance is useful if we want to find out what is the flow rate of a given fluid, either the hot fluid or the cold fluid. But it really does not give us any information of the heat exchange taking place between the hot fluid and the cold fluid in terms of the length of the pipe. Now that is an important term, the length of the pipe, because that allows us to design a heat exchanger. By design we mean how long should be a heat exchanger for a given heat transfer from, say, a hot fluid to a cold fluid. For that we will look at a separate module to see how the mathematics for that is developed.